So hello everyone and welcome to this meeting. As I communicated earlier, in this class we're going to discuss correlation and regression analysis. And as we mentioned is that these are two different topics, correlation analysis and regression analysis. So in the first part of our discussion, we'll be talking about correlation analysis. We'll be looking at what is correlation analysis and the various ways of studying correlation. Then later on, we'll be looking at regression analysis. We'll look at the definition of regression analysis and the various ways of performing regression analysis by hand. So what is correlation analysis? And correlation basically is coming from the word core and then relate. So core, of course, signifies two. Then it is from this word where we get the word relationship. So basically, when we're talking about correlation analysis, we are referring to a statistical analysis which measures and analyzes the extent to which two variables fluctuate with reference to each other. So in correlation analysis, we'll always be dealing with two variables. Then we measure the extent to which the two variables fluctuate with reference to each other. For example, you can imagine a variable which you can call x. You can say, hey, x is the height of the father. Then you can have you can have y as the height of the son. Then you may want to check how these two variables are related, or the extent to which maybe the height of the son will change once you change the height of the father, and so on and so forth. So basically, that's what we call correlation. So I was saying that you may want to look at the relationship that is there between the height of the fathers and height of the sons. Now, correlation can be studied both graphically and also algebraically. On the word algebra here, meaning that we use a formula, or you can use a graphical representation of data to understand the relationship that exists between two variables. So graphically, correlation is studied using what we call scatter diagrams or scatter plots. Okay. Then algebraically, we study correlation using various methods, including what we call the Karl Pearson's method and also the Spearman's method, among other methods. So in this class, our focus will only be the algebraic method that is suggested by Karl Pearson, and also the method that is suggested by Spearman. So what are scatter diagrams? And we start by saying that in order to ascertain the nature and strength of relationship between two variables, we plot the pairs of points on the XY plane. So we just do a plot of the two variables, of the pairs of points corresponding to the two variables. Then you observe the nature of plot that you have. And there are several scenarios that you can obtain when you do a scatter plot. For example, you can see scenario number one here. When you plot and all the points fall on a straight line, which is sloping upwards like this one. So if the points happen to be falling on a straight line such that you can join all the points using a straight line, then we say that those two variables, x and y, have perfect positive correlation. Another scenario is where you plot the points. There is evidence that they are sloping upwards. They are extremely close to each other, but they don't form a straight line. So there are points like this. They form a very narrow band like this one. Then if that is the nature of your scatter plot, you can say that there is high positive correlation. Then you can also plot the points. Then you notice there is evidence that they are sloping upwards like these ones, but the points are quite far apart from each other. So in such a case, you say there is low positive correlation. So as long as the points are sloping upwards or from the left-hand side, upwards on the right-hand side, then you say there is positive correlation. And positive correlation can either be perfect, can be high, can be moderate. Or even can be low. Now, on the other hand, you can plot the points, like in this scenario, and you observe that the points are forming a straight line, which is sloping downwards, like this one. So all the points are falling on a straight line, which is falling or which is sloping downwards. So in such a case, you say that the two variables have perfect negative correlation. Then if the points are sloping downwards and they are close to each other, they form a narrow band of points, but they don't form a straight line, we say that there is high negative correlation. Then finally, if you plot the points, then you observe that there is evidence of negative slope or sloping downwards, and the points are far apart from each other, you can say that there is low negative correlation. Then, sorry, this is the final one. If you plot the points and you notice that they are forming a circular band or they are forming a horizontal band, like this one, this is an example of a circular band. So there is no evidence of sloping upwards or downwards. If there is no evidence of upward or downward slope, then we say that there is no correlation between the two variables, or there is zero correlation between the variables. Okay, then we say that correlation is said to be positive if an increase in one of the variables corresponds to an increase in the other variable and vice versa. That is, if an increase in the first variable corresponds to an increase in the second variable, then we say that that is positive correlation. We're also saying that the vice versa is if a decrease in one of the variables corresponds to a decrease in the other variable, we're saying that this will also be positive correlation. So if the direction of change is the same for the two variables, then we say that there is positive correlation there. On the other hand, correlation is said to be negative if an increase in one variable corresponds to a decrease in the other variable and vice versa. That is, if you have a positive, if you increase one variable, then this is what happens to the other variable. And this one amounts to minus or negative. Then we're also saying that if you decrease one variable, then if that corresponds to an increase in the other one, in the other variable, then this corresponds to, this also results to negative correlation. So that's basically how you know whether the two variables have a positive relationship or a negative relationship. I have some two diagrams here to illustrate that story. And I have, this is my X axis, and then I have my Y axis here. Then I have this line here. Assume there are some points there, and then that line, it gives the relationship between the variables. So you notice that if I mark a point like this one here, and then I pick another point there, then the value of X corresponding to the first point is X1. And the value of Y corresponding to the other, to the vertical axis is Y2. Then the value of X corresponding to the second point is X2, and the value of Y corresponding to the vertical axis is Y2. So you notice that if I move from this point here, this is X1, I increase to this point X2, then what has happened to the values of Y? The values of Y have also moved from this point to that point. So this is a positive, which gives another positive. A positive corresponding to a positive. That's positive correlation. The same way, if I start from X2 going to X1 like that, that's a negative. That is decreasing the value of X. I've decreased the value of X from X2 to X1. Then what has happened to the values of Y? They have also decreased from this point to this point. So that's another negative. So these are negative corresponding to another negative. And that's what we said corresponds to positive correlation. So the first diagram here illustrates a positive relationship between X and Y, a positive relationship or positive correlation between X and Y. On the other hand, if you have, this is my X axis and this is my Y axis, and I have this line here, then I pick some 2 points. Let's say I pick this point here on the line and another point here on the line. Then the value of X corresponding to the first point is X1, and the value of Y corresponding to the first point is Y1. And the same case to this X2. The value of X corresponding to the second point is X2, and the value of Y corresponding to the second point is Y2. So if you pick this value of X, then you increase to this point here. Then we want to see what has happened to the values of Y. Values of Y have started from here, that's the first point, to the second point like that. So this is an increase, which has a corresponding decrease. So that's a positive and an increase. And we say this is negative correlation. On the other hand, if you reverse this movement such that this is negative, that's negative. So you're moving from the second point to the first point, you'll be moving from Y2 to Y1, which is a positive, which amounts to negative. So the second diagram here illustrates a negative relationship between X and Y. Then we notice that correlation is either linear, like this is a linear relationship because it's a straight line kind of relationship. We assume the points are there, or maybe they are on the line. So like that. So that is a linear relationship, a straight line kind of relationship, but it can also be non-linear. You can imagine of a scenario where the relationship between X and Y is like this. This is Y and this is X. So this is not a linear relationship. You may want to think that it is quadratic kind of relationship. And we can even have higher order kind of relationship, like cubic relationship, and so on and so forth. But for the sake of this class, we will restrict our discussions to only linear relationship between two variables, say X and Y. Okay, so that is how you study correlation graphically using the scatter plot. You just need to plot the points, then you make an assessment to say whether there is a positive relationship or negative relationship. If the points are very close to each other, you may want to say that the relationship is stronger. But if the points are more scattered, you may want to say that the relationship is weaker. Then after you say whether it is a strong or weak relationship, you have to mention whether it is a positive relationship or it is a negative relationship. Okay. So let's look at the algebraic methods of studying correlation. And here we're going to discuss the Karl Pearson's correlation coefficient, as well as the Spearman's correlation coefficient. So let's start with the Karl Pearson's coefficient of correlation. And this one is usually denoted by small letter r, okay? And the definition of Karl Pearson's correlation coefficient is as given here. So let me switch the display so that we can have some more details on the same. Yeah, so I was saying that Karl Pearson's correlation coefficient can be defined as this. The covariance of X and Y divided by, in short, you can say S of X multiplied by S of Y. Okay, where S of X is the standard deviation of variable X. And we all know how to obtain standard deviation. So this is the same as square root of summation of X minus X bar squared divided by N. And then S of Y, is the standard deviation of the other variable, which is given by summation of Y minus Y bar squared over N. Then COV xy, this is V, covariance, is the covariance of x and y, which is given by, the covariance is some arithmetic mean, which is given by summation of x minus x bar, y minus y bar. That, a summation of that product of deviations divided by n. Okay. So those are the guys we need to plug into the formula above, and then we come up with a complete formula for the Karl Pearson's correlation coefficient. So this item here can be rewritten as this summation of x squared minus n x bar square. The guy inside the brackets can be rewritten like that. This is x bar square. And this can also be rewritten as summation of y square minus n y bar square divided by n, like that. And in a similar way, we can also define the last item, which can be written as summation of x y minus n x bar y bar divided by n. Okay, so you can work out these items independently. Then this one, you plug it up there. Then you work out this item here. You plug it here. And then you work out the last value. You put it there, then you get the quotient. That should be easy. You will notice that it is easy for you to obtain the standard deviation, and I mean from your calculator, if you're using a scientific calculator. Then using the same calculator, it is easy to obtain these values. Summation of x squared, easy to get from your calculator. Summation of y squared, summation of xy, you can get directly from your calculator. X bar, you can get directly from your calculator. Y bar, you can get directly from your calculator. Meaning that the items that are in this formula here are quite easy to obtain even from your calculator without having to do so many calculations. Okay, so basically that is the formula of the Karl Pearson's correlation coefficient. There are various ways of expressing it, but this is the idea. This is just the idea. Okay, so let's go back to the other notes, or the other set of notes. And this is the same story. As you can see, the last expression here is based on the expanded format. It's based on the expanded format because you can, if you look at this item here, then you have this item here, and then you have this item, and this. If you work with these three items, this item, this one, and this one, if you plug them in to this formula here, you will end up with this formula. Because the n's will cancel in a way. The n will cancel. So you are left with a formula like that, which you can now see why it can be expressed in this format. Okay. Then we note that, so that we shall be applying that in a short while. So we notice that R is a number which ranges between -1 and +1. So the correlation coefficient is always a number between -1 and +1. That means if you draw the number line like this, and this is your -1, this is your 0, this is your +1, then R is a number within this interval. R is a number within that interval all the time. So let's have an example. And we're saying that find the Karl Pearson's correlation coefficient for the following data. So we are considering this data. We want to find the Karl Pearson's correlation coefficient. I want us to copy this data, then we're going to solve the question in a short while. So this is the example we are solving. And this is the formula that we are going to apply to find the Karl Pearson's correlation coefficient. So I want us to use our calculators, our scientific calculators, to obtain these values: summation of x, y, x bar, y bar, n, of course, but you know n is 7, summation of x square, summation of y square. Then once we get those values, we plug them in here, then we get the required value. So in order to solve this problem, we need to obtain these items. And we can quickly obtain these from calculators using the regression mode on FX82 calculator, or using the start mode in the other calculators. So once you use the regression mode, you'll choose linear regression, the number corresponding to linear, say the lean or linear like that. You choose the mode that corresponds to, the value that corresponds to that option. Okay. Then once you choose the correct mode, you enter the values. Like if this is the calculator you are using, you are going to enter the pairs of observations starting with the x. Then you separate them by comma. So you have x, the value of x, comma, the value of y, then you press m plus. For example, you will type 64, 66, m plus. When you do that, you will see that you've entered one observation. Then you go to the next value, 65, 67, m plus. When you do that, you'll see that you've entered 2 observations. You continue like that up to the last pair, which is 70, 62 followed by m plus. So that's how you enter the data, especially if you are using the FX82 type of calculator. If you're using the other type of calculators where the mode is called start, once you choose this mode, it will lead you to several options. So you need to choose the one that looks like this, A plus B of X. That's the regression mode. Then you will see a table. You will see a table where the first column is X, the other column is Y. So you key in the values. You can start by keying the values of X. Once you type the given value, you press equal sign. For example, you press 64 equal sign, then you'll see 64 come up here. 65 equal sign, you will see 65 come up here, all the way up to the last one. And once you are done with the values of X, you can come and key in the values of Y in a similar way. So 66 equals, 67 equals, and so on and so forth. So the data in this case will be in form of a table like this. So once you've entered all the values in the memory of your calculator, you need to go to sum. You need to go to sum. There is one of the keys on your keypad, on the keypad of your calculator is sum. It is either sum or start, depending on the calculator that we are using. So once you press sum, you will see several options. You will see summation of x square, summation of x, and n. So those are number 1, 2, and 3. If you press the right navigation key, the biggest key on your calculator, if you press the right-hand one to navigate far right, you will see additional options, summation of y square, summation of y, summation of xy. And those are the values that we need here to use in our calculations. If you don't want to do that, you can still do this question manually by coming up with 2 columns, x and y. That's the given data. Then you need to have a column for x square. So you square the values of x. You also need to square the values of y. Then you need the product of x and y. Then down here, you need this summation. So you need this summation of x square. You need this summation of y square. You need the summation of x, y. But in addition to this, you need the value of x bar, which is summation of x divided by n. So here you also need summation of x, and you also need y bar. You also need y bar, which is summation of y divided by n. So meaning that you also need summation of y there. So you can do it manually by coming up with a table like this, and you complete those columns as indicated there. But if you know how to use the calculator to obtain these summations, it will be easier for you if you're able to get it like this. It will be easier like that. Okay, so so let me record the values that you are obtaining from your calculators. then you can use them in the formula given here. Summation of x?
469.
Then somebody else, summation of y?
476.
Then summation of xy? So after obtaining the values, now we plug them into the formula. So we say that r is equal to, let me record the formula, xy minus n, x bar, y bar, divided by summation of x square minus n, x bar square, summation of y square minus n, y bar square. That the divisor is square rooted like that. So this is that 917 minus n is 7 multiplied by x bar. We didn't get x bar, so we need to get x bar. You saw the values of x bar is 67 and the value of y by 68. So plugging them in here, we have 67 here multiplied by 68. Divide everything by that 1451 minus n, which is 7, and 68, 67 squared. The space is not enough here, so let me write on the next page. So we're saying R is equal to at 917 minus 7, 68, 67. Divide this by that 1451 minus 7 times 67 squared. Multiply this by 32402 minus 7 in 68 squared, like that. And then you take square root. You take square root. So when you simplify that, you'll get the answer is 0.81 rounded off 2 decimal places. And for correlation, you always include the sign, whether it is positive or negative. Just like you saw in the case of the scatter plots, we say whether correlation is, or whether the relationship is positive or negative. So even when we are using algebraic methods, you indicate whether the answer is positive or negative. So that is the Karl Pearson's correlation coefficient for the two variables given there. So how do you interpret this? How do you interpret this? And as we mentioned earlier, is that the correlation coefficient is always a number between -1 and +1. So meaning that 0 is at the center there. If it happens that your correlation coefficient is at this point here, is -1, then we say that there is perfect negative correlation. If it happens that your variables, I mean the value of the coefficient of correlation is -1, we say there is perfect negative correlation. On the other hand, if it happens that the value of your correlation coefficient is +1, we say there is perfect positive correlation. If it happens that the value of your correlation coefficient is 0, we say that there is no, or there is 0 correlation. The two variables are not correlated at all. Those are very rare scenarios. So in most of the cases, you will find yourself away from those 3 points. So to help us in interpreting correlation coefficients, we can partition this line segment into several parts like that. So you can say this is minus 0.3, points below 0. This is minus 0.7, then plus 0.3 and plus 0.7. You can partition like that. So we can say that if the value of correlation coefficient lies within this interval here, you say there is low negative correlation. If it lies within this interval here, between 0 and positive 3 and positive 0.3, you say there is low positive correlation. Okay, so if your value of correlation lies within this interval here, that is between plus 0.3 and plus 0.7, you say there is moderate positive correlation. There is moderate positive correlation. If it happens that the value of coefficient of correlation is between minus 0.3 and minus 0.7, you say there is moderate negative correlation. Then if it happens that your correlation coefficient is a number between minus 0.7 and minus 1, you say there is high negative correlation. And on the other hand, if your value of correlation of coefficient is between plus 0.7 and plus 1.0, we say there is high positive correlation. So we can use that chart to interpret given values of correlation of coefficient. For example, in our earlier illustration there, we got R is plus 0.81, which clearly falls in that interval. So we can argue that there is a high positive correlation between the values, between the variables X and Y. So that is the interpretation of that value of correlation coefficient. Okay. So next, I want us to look at the Spearman's rank correlation coefficient. And as mentioned in the class notes is that the Spearman's rank correlation coefficient, which is denoted by the Greek symbol rho, is preferred in cases when you are dealing with qualitative variables. Okay, when we're dealing with attributes like beauty that cannot be measured quantitatively, or attributes like intelligence, which cannot be measured quantitatively. So basically what you do when you're given a set of observations, you rank them. Then you also allow somebody else to rank them independently. Then now you analyze the ranks and check whether they are agreeing to a great extent or they are disagreeing to a great extent. Now, the formula that we use when we want to find the Spearman's rank correlation coefficient is rho is equal to 1 minus 6 summation of d square divided by, you can have n cubed minus n. In some cases, the divisor will look like this, the same thing. So this is a formula for the Spearman's rank correlation coefficient, where d square is the square of the difference, is the square of the difference between pairs of corresponding ranks. Pairs of corresponding ranks. So like ranks from the same individual. Okay. Then of course, when you talk about sigma, d square is the sum. Is the sum of this. Sum of the squared differences or sum of the squares of differences between pairs of corresponding ranks. Then n is the number of observations. N is the number of observations and 6 is a constant, is there in the formula. So let's have an example. I want us to find the Spearman's rank correlation coefficient for the following data. So let's consider this data and obtain the Spearman's rank correlation coefficient. Now, the first thing is to rank the observations in each variable. So we can have ranks of X. So let's rank these values. We can decide to assign rank number 1 to the largest value. So in the column of X, the largest value is 95. So this one will be number 1. Then number 2 will be 90. It's 9. Then this will be number 3. Then this will be number 4. Number 5. Number 6. Number 7. So what we've done, we have just ranked the values of X such a way that the highest value is given rank number 1. You can do the reverse. You can assign the smallest number, you assign it number 1. But if you do that to X, do the same to Y. So let's also rank Y. So the largest value in Y is the number 150. So this is rank number 1. So I want you to imagine a scenario where I have 1, 2, 3, 4, 5, 6, 7 students, and I have their tests marked by 2 lecturers. So there's a lecturer called X, another lecturer called Y. And the numbers indicated here are the marks awarded by the different lecturers. So you want to see, if you are to rank the students, will there be consistency in the way the students are ranked according to their performance? So you notice that, like in this case, the student who was identified as number 1 by lecturer X is the same student who was identified as number 1 by lecturer Y. So there's some consistency there as far as that student is concerned. Then continuing with the rankings of Y, number 2 is 140. So this is your number 2. You can see the other lecturer ranked that person as number 4. Then number 3 is there. Number 4. Then number 5. Number 6, there's no change. Number 7. So those are the ranks of the 2 variables. Now, what we're calling D is the difference. We said it's the difference between pairs of ranks. So for example, here it will be 3 minus 4. That's D. 2 minus 3. That's another D. So, but we want to have it squared, so that we don't have some negatives. So 3 minus 4, this will be 1. This will also be 1. This will be 0. This will be 0. This will also be 0. This will be 4. And this will be 0. So when you sum these numbers, we'll get summation of D square, which is 6. Okay. Then we said that rho is 1 minus 6 times summation of D square, which is 6 square. Which is 6. Which is 6 divided by number of observations. And how many observations do we have here? 1, 2, 3, 4, 5, 6, 7. Yeah, so you have 7 cubed minus 7. And when you simplify this, you'll get this is plus 0.89 something, 892, 893. So that is the Spearman's rank correlation coefficient. The interpretation is similar to what we saw earlier on. So you're going to use the same criteria here, or scale, to interpret that value of plus 0.89. Okay, so that is basically how you perform correlation analysis. Any question there?